Okay, so I started recording. So again, you know, I'm trying to get you to think about, you know, when you go out to work, and part of what I'll do, and again, getting more and more stricter in the third and fourth semester, is getting your work to be more and more professional, so professional looking, so that, you know, when you put together a resume in your third or fourth semester and you're going to go out to get a job, that should be like a picture perfect resume, because first impressions are lasting ones. And, you know, especially when the economy is tight and they're looking for jobs, you know, somebody once said to me that a hiring person in HR looks at a resume for about 10 to 15 seconds. At the end of that 10 to 15 seconds, it either goes on the let's look into it further pile or it goes in the garbage. So any little mistakes is going to be that excuse to say, you know, this person isn't worth the effort to look at. So I'm trying to get you into the mode of thinking about being professional in all that you do, which means getting here on time, which means doing stuff at a professional level and all that kind of stuff. So, okay, enough said about that. So let's go back to, we can get rid of RTFM because we don't need that anymore. Last week we talked about how do we go about the process of converting between different powers of 10. And we talked about the process we did. We did a number of examples. I did a couple of examples on how we do that. And we said that we're going to basically put in the 2 powers of 10, replacing the prefixes with the powers of 10. If we're going to a larger power of 10, we move the decimal point to the left. How far we move it to the left or to the right is a function of the difference between the 2 powers. So in this case, we were going from 10 to the -6 to 10 to the -3. -3 is larger than -6, so we're going to move left. And the difference between these two is 3, so we moved it 3 places to the left. If going to a smaller power, we move to the right by the difference, right? And then you did a couple of examples. We converted, and we had a bunch of stuff there. What I want to do today, we're done with that. What I want to do today is look at the circuit. We briefly talked about batteries, and we talked about light bulbs, and we talked about my mouse go? And we talked about a complete circuit. So what we had drawn was something like we had a battery.
The screen is no longer showing.
Yep, thank you. So we had a battery, and we said we had a positive terminal and we had a negative terminal. And we said that over here we had, oh, hold on one second. This is the department chair. Hi, can I call you back? I'm in class. Okay, bye. Okay, so we had the battery and we had a light bulb and we had a complete circuit, and we said we had charges, positive, the net positive charge moved from the positive to the negative. What we want to do today is start to look at some of this stuff and say, wait, let's look at this from a more realistic viewpoint. This is almost like a pictorial diagram. And what's my alternative to that you probably talked about in the lab already? What kind of a diagram? You can unmute yourself if you have an answer. I muted everybody before. Did you talk about a schematic diagram?
I don't think they did.
Okay.
So.
All right. So what you can do is you can draw what's called a schematic diagram. And what that does is it uses symbols in place of pictures of objects. And we call those symbols, we call them schematic symbols. All right, and very quickly, let's go through some of the schematic symbols. We already used one in our little diagram over here. If I have a battery, the schematic symbol for that is going to be a short line, a long line, a short line, a long line, a short line, and look something like that. The long bar is the positive terminal, the plus end. The short bar is the negative terminal. Or the minus terminal. Just as a general rule, the positive wiring usually uses red wire. And the negative terminal, or the negative wiring, usually uses black wire. All right, so if I was wiring up a circuit board or a proto board, which you'll learn about in lab, I would always try and make my wires that go to the positive lead of the battery red, and I try and make my wires that go to the negative lead of the battery black. So that when I look at a circuit and I see a red wire, I'm going, that's a battery voltage. Or I see a black wire, I say, oh, that's the negative of the battery. And any other wiring in between that I might need would be a different color other than red and black. So that's our battery symbol. If I have a lamp or a light bulb, you'll see sometimes different symbols. Most of the time, you'll see something like that. Sometimes you'll see them drawn that way, especially if it's on a computer. Sometimes you'll see something like that. The idea is that the loop, in any of the cases, represents the filament. And the way a light bulb works is current flows through the wire inside the bulb, gets it hot enough that it glows, and that glowing part is called the filament. And then the circle would represent the glass around the light bulb. Okay. One of the other components that we're going to talk about is a resistor. Now, the textbook has a whole boatload of different kinds of resistors. I'll give you a minute to jot this down, and then I'm going to share a different screen just to show you some of the different kinds of resistors. You looked at them. Did you measure them in lab the other day?
Yes, we did on first day.
Okay, so you've seen some resistors already.
Yes.
Let me show you a couple of other different kinds of resistors. Just need to pull up a file. Had it, then lost it. I spoke, let me just talk about this very quickly. I sent an email to the department secretary and had her check, and the books have been ordered, but I'm not sure when they're going to be. I sent another email this morning saying, do we have a date as to when you're going to be able to access the books? Because I think they're, they're ebooks. And I'm still waiting to hear back. And I would imagine that maybe the chair had a something to say about that when she just called. So I'll wait until the break. When we take a break, I'll see if we can find out what's going on. Okay. Let me share a different screen. Actually, let me hold this screen for a moment. So the symbol for a resistor looks something like that. Remember, the resistor is the opposition to current flow. So I guess what they thought was if I had a nice straight wire, current could run nice and easy. And if I wanted to symbolize that it's not as easy, I'll put some turns in it. Not that that affects the flow as much as it's a visual thing that says it's harder to get through. So that's the symbol for a resistor. Technically, if you really wanted to get picky about it, this line is at a 60-degree angle from horizontal. There are 3 points on the top, 3 points on the bottom. Having said that, if you follow this as a career, you're going to see resistors that people draw on blackboards that look anything like that to that. But try and do, again, we're talking about trying to maintain a professional way of looking at things. So as you draw resistors, try and keep them professional looking. Let me share a different screen and we'll go through a couple of the different kinds of resistors you're liable to see. There we go. All right, so there's the symbol for a resistor. Some of the different kinds of resistors you're liable to see. These are the ones you probably looked at, something similar to these, or we'll see another one in a minute. And these are all pictures out of the textbook. So when you get the textbook, you don't try and draw all of these. But there's two broad categories we'll talk about when we look at resistors. And one of them is called a leaded component. Where am I? So we have a leaded component, and as the name implies, there are leads on it. All right, hold on. Somebody needs to get into the room.
What is a lead? Is that just the
Okay.
lead wire?
Yeah, so the lead is this wire that comes out of the component. All right, we call those the component leads. And one of the things that you'll notice is if I look at this little resistor, the lead is thinner than the next resistor, and that lead is thinner than that. These are all pretty much the same size leads, maybe the bigger one. Maybe the bigger one might be a little bit thicker, but it's important to know that we're going to work with something called a proto board. Let me hold on one second. So I don't know whether or not you can see that. Let me get it tipped right. All right, so this is what they call a proto board. And what that proto board is a plastic board that's got some metal contacts, and they're in rows of 5. Let me see if I can.
It's in the green screen.
Yeah, hold on. Let me get rid of my. Okay, so what you've got is a proto board, and I don't know if I can get that clear enough. But what you've got is rows of 5 contacts that go across that are all connected underneath. And what you can do is, like you see over here, I've plugged a wire into a contact here. Actually, this is a diode. I've plugged one wire in over here and one wire in over here. So I've made contact. What I was getting at with all of this is when you use these proto boards, if you push, let's say, one of these wires, or actually one of these wires into the proto board, it'll bend the contact inside and possibly damage the board. So you want to be aware of the fact that these leads, there's limits to how big of a lead you can push into a proto board. These are different size resistors, physically different size resistors. And did you go over color code yet?
Yeah.
So this is orange, 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 yellow, or gold. This is orange, 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 gold, orange, 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 gold. So in terms of the resistance, how many ohms of resistance these resistors are, same or different? What does the color code tell us?
The same.
It tells us the resistance, which would mean that if these are all orange, 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 gold, they're all the same number of ohms of resistance. The difference is the amount of power that they can, what they call, dissipate. When you have current flowing through a resistance, you're going to generate heat. The more heat you generate, the hotter something's going to get, which means we have to get rid of that heat. Well, if I have something little like this guy that doesn't have a lot of surface area to get rid of heat, I can't get rid of as much heat here as I can with something down on the bottom that's nice and big. A lot of surface area to get rid of heat. So the power rating, the amount of heat we can dissipate, determines the size, or actually the size determines the power rating. We'll talk about power in chapter 4 and energy in chapter 4. But all of these resistors are the same number of ohms. They're just different size because this guy could dissipate a lot more heat, which means it can carry a lot more current than this guy, which is a lot smaller. So each time we get bigger, it can dissipate more heat. Okay, so these are what we call leaded component. Okay, the next possibility is lead-less components. Because they don't have a wire lead coming out of them. You notice here that there's no wire lead on this little square thing. And these leads over here are not really designed to go into a circuit board. This, by the way, is sometimes called a through-hole component. And it's, boy, the phone's ringing off the hook today. It never rings. A through-hole component, the way this works is, let me just get a different color. So envision, here's a printed circuit board. The printed circuit board has copper on the bottom. So this is copper, and that copper connects to other components to complete that circuit. So this copper is like the wire that we would have in a normal circuit. There's a hole that goes from the top of the board through the copper on the bottom. When you have a leaded component, so envision we're taking this much of the component. So you have the component sitting over here, and the wire comes in and goes down through the hole and comes out the bottom. Hence the name through hole. Goes through the hole. What they do at that point is, you're going to do soldering, I think, today. What they do is you'll heat up the copper and the wire and put solder on it, which is a mixture of tin and lead, or lead less, depending on the kind of solder you got. And you make a connection. So now this, let me go back to a pointer. So now this lead and this copper are connected, electrically connected together by the solder. Okay, everybody with me on that? So if I looked at the bottom of a circuit board, I don't think I have a circuit board handy.
Master, did you say solder is a mixture of tin and lead?
Tin and lead.
Isn't lead dangerous?
Yeah, which is why most countries today have eliminated lead-based solder. The United States eliminated the solder, that tin and lead mixture was what was used in water pipes for years and years and years and years. And now all of the plumbing standards have said you can't use lead anymore in soldering pipes together. Admittedly, the amount of lead that you would get leaching out of a solder connection in a pipe is very minimal. But they actually had, back 100 years ago or more, they actually did bring water lines into houses on lead pipes, which we know today is like, if you even suggested that, they'd go, you can't do that. But back 100 years ago, they didn't know what lead could do. So today, most solders that are used are not lead-based. And I don't know what you've got that you're going to use in lab when you do it, but if you have to use a lead-based solder, definitely, you know, you want to stay away from inhaling the fumes, and you definitely want to wash your hands as soon as you're done with doing the soldering.
It's lead based on that we're gonna use.
I don't know what you're going to use. Let me, hold on one second.
I have it right here.
Yeah, it is lead based, the one that they gave us in our kits.
Oh, is it?
The lab has
Yeah.
lead ones, yes.
Let me,
Well, that's concerning. Okay.
okay. So if I look at this circuit board that I'm holding up here, on the end over here, there's This is very hard to do because I'm on this one. Over here on the end, there are two leads that have to get connected to the bottom. So if I flip over the bottom, you can see where those two leads have come through the bottom of the board and have been soldered. And admittedly, it's not very in focus, but you can see them. So that's the way the soldering works. More and more, we're going to something called, which is what the other one is. Let's go to here. The leadless version, which is sometimes called a surface mount. Device. One of the things you're going to learn about the field you're going into, the field of electronics, is that it's acronym city. You already learned an acronym today, RTFM. Surface mount device, you'll look down here and you'll see SMD. SMD stands for surface mount device. And the way a surface mount device works is, now what we've got is we've got our circuit board and we've got our copper on the surface board, but now it's usually on the top of the surface board. So there might be copper there, and we might have copper there. And what we do is, let me give you 1 second. We put, where am I? We put our component right on the board. Now, a lot of times what will happen is, this is all done by machines these days. It's called a pick and place machine. What they'll do is down here, once I can figure out where I am, down here, they'll put a dot of basically crazy glue. What'll happen is the component will be pressed down onto the crazy glue, and that holds it in place when it's getting ready to be soldered. So what we've done is basically taken this guy and put it on a circuit board. This end cap over here is over here. Well, actually that one is there and the other one's over here. But you got the two end caps. What happens is they'll put down solder, and the solder will now flow from the end cap onto the circuit board, onto the copper. And there's a lot of reasons why, and this one, let me talk about that one for a minute. The one that you see like that has a lead that comes down like that and touches the solder. Touches the copper. So the lead comes down and touches the copper. This is the copper, this is the lead. And again, we get that soldered on there. So there's no through hole. It's mounted on the surface of the circuit board, hence surface mount. Okay. More and more they're going towards surface mount. And there's a lot of reasons for that, some of which you'll get into maybe when you're in some of the circuits courses at ELT112, I guess it is, as to why it's much nicer to have surface mount than it is for copper. One of the reasons, key reasons, is if you look at the size of this resistor, and this is not to scale, this resistor is probably 3/8 of an inch long. No, almost a 1/2 inch long. This one can be less than 1/4 of an inch long. So it's a lot smaller. So it takes up a lot less real estate on a circuit board, which means I can make my circuit boards a lot smaller. If it wasn't for surface mount devices, you wouldn't hold one of these in your hand. The first telephones, they used to call them a brick because literally they were probably, envision a ring binder and maybe a little bit smaller than that, but wider than that. That's how big they were. Okay, enough of a divergence. All right, so let's go on to the next slide. We could also put multiple resistors inside of one package. So this is called a resistor, a chip resistor array. So what that might mean is you've got something like, oh, I didn't want to do that. You might have something like this. You might have one resistor, two resistors, three resistors, four resistors, or so, or more. And all of those are inside one package. So you've got a lead for one, the other end, a lead for the second resistor and its other end, a lead for the third resistor and its other end. So all of these, envision it this way. And so on. Okay, so they, oh, yeah, okay, we are. So envision that that's the way that one works.
Professor,
Yeah,
when you go back to that picture, are the resistors going through the little like holes, like you see the little concave holes on the side? Are the resistors going through those, or are they resting on the flat side like you drew them?
the resistor contact. So in other words, this, let me go back to a point there, hold on. This section here looks like this section in the individual resistor. So this would be a contact for a resistor with the other end being there. This would be a contact with the other end being there. This would be a contact, the other end is there. That cleared up?
It's like 4 like chips.
Now these would be
What about the
5
concave
resistors.
area?
Say again? I didn't hear.
What about that concave area?
That's just a spacer so that the solder probably doesn't flow from this one to this one when they solder it.
Okay,
Just a break.
so that just stays there. Okay.
All right. And we see something similar to that in here. Again, this is the same kind of thing. You might have one resistor going from this pin to this one, another resistor going from this pin to wherever the other one is over here, and so on and so forth. They can also do a resistor network where they have one common terminal. So a lot of times if we're using a 7-segment display, like you see on an alarm clock or whatever, they might have something that looks like something like that, where all of the resistors are tied together along one side. So this is what we call a common connection. All of the resistors along that side are connected together. And then we bring out down here the individual leads for the individual resistors. So if we looked at the resistor network, that one that's labeled SIM, you might see something like, if we envision what's inside, you might see something like that, where this is the common connection, and this would be resistor 1, resistor 2, resistor 3. Okay.
Can you explain common connection?
It's where they're all connected together. So in other words, if I look at this resistor, and 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 this resistor, the top leads are all connected together to one lead that we bring out. That's called a common connection. We say that this wire is common to this resistor, and to this resistor, and to this resistor, that one, and that one. So that's what we call a common connection. Go ahead.
Okay, so the resistors are basically the things that are basically like opposing the current, right?
Yes, they're all opposing current. Yep.
Okay.
And we'll talk about where they're useful. We'll do some examples with that in a couple of minutes. Not in a couple of minutes because we're going to be out of time in a couple of minutes. But so anyway,
for the common connection. Oh, sorry.
Go ahead.
Just wanted to ask, for the common connection, is that where like the entire like net current, like the net voltage is, or is that going to be where after the current like passes through all of the resistors, that's where it's going to be where that pulls up?
Well, it depends on how we connected, but let's say we connected each one of these leads up to the back, to the positive terminal of the battery. Then whatever current flows through that resistor has to go through the common lead, and whatever has to go through this to the common lead, and whatever. So in other words, this common lead is going to have the current from this resistor, this resistor, this resistor, this resistor, this resistor, and that resistor. And we'll see that this lead is going to have the total of all of these currents flowing through it. But we'll talk about that. That's getting a little ahead of it.
Okay.
Very quickly, if we think about how resistors are made, that chip, the SMD, sometimes a resistor like this, let me just change my color back. This type of SMD is also sometimes called a chip resistor. Because it's used with integrated circuits, which are sometimes called chips. And what they do is, the way they make that is, there's a ceramic substrate. Let me go back to pointer. There's a ceramic substrate, and that's nothing more than a mechanical thing to put our resistive element on. So the resistive material, sometimes carbon, sometimes a metal, goes over that, and that's where the actual resistance, the opposition, comes from. All right. And then we cap it with a protective glass coating, and we bring our external caps on the end to make connection to the resistive material on this end and a connection on this end. So you're always going to have some sort of resistive material and some sort of support for that resistive material. So in this picture, the resistive material is blue. The support would be the ceramic stuff underneath it. Because if it wasn't there, this would break very easily. If I look at the next one.
What is the ceramic substrate?
Ceramic, this is the ceramic substrate. Substrate means
yes, but like
put below. So this is a ceramic layer below.
substrate means what?
A ceramic substrate is a substrate is a layer you put below something. So in other words, you have your
Okay.
resistive material, and below that you have your ceramic material. So
Okay.
this is our mechanical support. This is our resistive material. If I look over here in this one, the carbon composition resistor, this is a mixture basically of carbon and clay, which gives us the resistive part. The lead gets embedded in the end of it, and then we put an insulating coating around the outside to give it the mechanical strength and protection. Okay, so that's the way that one's made. We can also make it, again, using a ceramic. Usually this is a ceramic base, except now this is a cylinder, a ceramic cylinder. And what they do is they coat the ceramic cylinder with a thin metal or carbon, and then they use a helical, they actually use a knife to cut a spiral. So what we've got here is a spiral of the carbon or metal that goes around from one end to the other. And that's where then we put the connections on the either end. And these are called metal or carbon film resistors. These are what are becoming more and more and more popular for some advantages over carbon composition. For years, this used to be the way we made resistors.
Professor, can I ask you a question?
Sure.
Like how they put the power, like how they put the values on the resistor, like the one in the clay and so
in other words, how do you get
yeah,
500
how
ohms of resistance?
how we put like the value on those.
Well, what you do is, depending on how much carbon, so let's say this is a carbon clay mixture. Clay is pretty much an insulator. If I mix more carbon in and less clay, I'm going to get lower resistance. If I put less carbon and more clay, I'm going to get higher resistance. And I'm not sure, I keep meaning to look this up and I never do. I'm not sure whether or not they mix it and know exactly what they're going to get, or they mix it and then measure from end to end and then say, okay, this is a 500 ohm resistor or a 300 ohm resistor or whatever. I'm not sure about that. I have to double check.
How they like find the ratio? It's like a ratio stuff.
But yeah, it starts out with a ratio of the carbon to whatever the insulating material is on the inside.
Okay.
So, but this used to be the way we made resistors for years and years and years. But there's some disadvantages to this, and which is why we're going to more and more of the metal film resistors. We talked about this. This is the same kind of thing through hole. When we get to very, very large resistor, large power rating resistors, we need to be able to get rid of a lot of heat. And one of the things that this book doesn't show, unfortunately, is scale. So even if I went to this resistor here is probably maybe 3/4 of an inch long. So, and that's the biggest out of all of them. And if I went to this guy is probably 2 inches long by a 1/2 inch by a 1/2 inch. So it's a lot bigger. And this one can be huge. This one can be up to a couple of inches across and several inches long. So, you know, you look at this and you look at this and go, oh, this isn't that much bigger than this. Well, yeah, it is. It's considerably longer and it's considerably bigger in diameter. This one is designed to dissipate heat. So what you've got in here is the resistor is in here, but this whole piece around the outside is metal. And if you look, these are like little fins. So the heat that comes out of the resistor goes into the metal and it's dissipated into the air by the metal fins that you see here. And this also screws to a metal plate, sometimes the cabinet or the metal at they call it the chassis that the circuit is built on, and that helps to dissipate heat. Okay. You talked about resistor color code, so I'm going to stop here. I wanted to get further, but we didn't. But what we got through is important. What we'll do next class is we'll start saying, okay, we got resistors. We might look at a couple of other oh, I want to look at potentiometers. Then we'll actually start getting into circuits and using Ohm's law, and we'll see how what we looked at last class, where we were talking about manipulating powers of 10, how that can come in useful when we're doing calculations in a circuit. Okay. So in the meantime, I'm going to try and find out. If I find out anything about the book, I'll give you an email. I'll shoot out an email about the book. Okay. And I also, somebody asked about the video for last class. I edited the video, and yesterday was a crazy day. It was my wife's birthday, so I got nothing done. I will post those videos later tonight. Okay. So last class and this class, I'll post tonight. All right. Any questions on anything we covered? Okay, if there are no questions, see you on Thursday. Have a good weekend. Stay safe.
You too, bro. So thank you.
All right, you too. Thank
Professor,
you.
how long will the quiz take to get graded?
I should have that tonight because it gets done automatically. The program I use, one of the reasons I like using that program is I take the quiz and then I say grade the quiz, and it says, what are you going to use as the key? I click on my solution as the key and it grades it. And then right after that, I can send out the emails with your grade. One thing is very important when you're taking the quiz, make sure you type your email right. Because if you mistype your email, whoever that is that's got your mistyped email, that's who's going to get your quiz grade.
It was
Also, make sure you've got the Tuesday link and the Thursday link. Whatever email it was for Tuesday, that'll be our link for the entire semester. Whatever it was for Thursday, that's our link for the entire semester.
Okay.
You got it.
All right. Thank you.
Okay.
Thank you,
Thanks.
brother.
See you on
Have a
Tuesday.
good one.